Okay, in today's video we're going to be learning how to take the square root of complex numbers. Now we've learned before, we learned in our first lesson of complex numbers that we can take the square root of negative numbers, such as the square root of minus 4 being 2i. But what if we wanted to find, say, the square root of I, or the square root of 1 plus I? I'm going to follow a process that we're going to learn in this video of how to take the square root of complex numbers. Before we do that, we're going to quickly learn how we can equate both real and imaginary components. So one of the most useful go-to strategies to solve equations involving complex numbers is by equating the real and imaginary components separately. For example, if a complex number a plus ib is equal to I, well, we can say that's equal to 0 plus 1i. So the real component of this complex number is 0, and the imaginary component is 1. So for this complex equation, a is 0 and b is 1. So we have some special notation for that, rez and mz. So the real component of z in the first one, and I probably should say that they're all equal to z, but I don't have enough room. The real component is 3, the imaginary component mz is 4. Importantly, it's not 4i, the imaginary component is 4. Here the real component is the square root of 3, and the imaginary component is minus 2. In this one, the real component is 4, and the imaginary component is 0. And in the last one, the real component is 0, and the imaginary component is 5. Okay, we can use that to solve complex equations. So we've got the equation a plus 2 plus ib minus 3i is equal to 4 minus 2i. What we do is the process of this is called equating the real and imaginary components. So the real components on the left-hand side have to be equal to the real components on the right-hand side. And that's because we can never combine real and imaginary components. So a plus 2 has to equal 4. In a similar way, the real components, the imaginary components on the left-hand side of the equation is b minus 3. And on the right-hand side, it's minus 2. So solving those two equations, we get a is equal to 2 and b is equal to minus 1. And we're done. Okay. Find real numbers x and y such that x plus iy minus 2 minus 3y is minus 13i. Same process here, we're going to expand. So 2x minus 3ix plus 2iy. And that's going to be plus 3y. And that's equal to minus 13i. Now by equating the real and imaginary components, the real parts of this on the left-hand side are 2x plus 3y. And that has to equal 0. So the real components on the right-hand side, there aren't any there, so it's 0. The imaginary components on the left-hand side are minus 3x plus 2y, and that equals minus 13. Okay, we have a go at solving this simultaneous equations. We might make x the subject of this first one here. So x is going to equal minus 3 on 2y. Substitute that into my second equation. Minus 3 times minus 3 on 2y plus 2y equals minus 13. So minus 3, so we've got minus 9 on 2. Y plus 2y equals minus 13. So minus 9 on 2 plus 2 is minus 5 on 2. So we've got 5y on 2 equals 13, cancelling out those negatives. So 26 divided by 5, so y is 26 on 5, and x is just minus 3 on 2 times 26 on 5, which is minus 39 on 5. Okay. The square root of complex numbers. So we've determined already things like the square root of minus 4 equaling 2i. But what about root I, or root 2 plus 3i? A little formula here, and this is something you need to remember. If z is equal to a plus ib, then its square root x plus iy will satisfy x squared minus y squared is the real component of z, and 2xy is the imaginary component of z. That will form a set of simultaneous equations that we will solve for x and y. So we're going to solve, and we're going to find the square root of 3 plus 4i. So using our formula, x squared minus y squared is equal to the real component of 3. And 2xy is equal to the imaginary component of 4. All we have to do here is solve this set of simultaneous equations. So if we divide and make y the subject, we've got y is equal to 2 on x. We're then going to substitute that into my original equation. 4 on x squared minus, sorry, that's wrong. X squared minus 4 on x squared, so we're squaring that because it's y squared, is equal to 3. If we then multiply everything by x squared, we get x to the power of 4 minus 4 equals 3x squared. And x to the power of 4 minus 3x squared minus 4 equals 0. Now, hopefully you guys have the ability, and if not, you can do a u substitution to solve this, but I'm personally just going to factorize this, and we're going to have x squared minus 4, x squared plus 1 equals 0. Now, solving that, we've got x is equal to plus or minus 2, or x squared equals minus 1. Now, we're not going to care about this solution because we're told that the x component of the square root of complex number is real, so we can't have any imaginary solutions for x. Now we're going to solve that for y, so we know y is equal to 2 on x. So substituting that in, we're going to have y is plus or minus 1. So therefore the square root of my complex number is plus or minus 2 plus or minus 1i, which we often just say is plus or minus 2 plus I. Now, unfortunately, your calculator can't do this. It's one of really the only things that it's a lot of things it can't do, but this is one of the things that it can't do. However, I would definitely be getting your calculator and squaring 2 plus 4i and seeing if you get 3 plus 4i. Okay, there was not an error with that question, but it's not the particular example I was looking for. So correct your example to be this one in your booklet. So to solve this, we're going to say z, using the quadratic formula, z is 1 plus or minus the square root of b squared, so 1 squared, minus 4 times 4 plus 2i, over 2. So 1 plus or minus, let's figure out what's underneath that square root. We get the square root of minus 15 minus 8i over 2. Now that's not good enough as an answer. We need to take the square root of minus 15 minus 8i, and we're going to use that strategy that we just learnt. So x squared minus y squared equals the real component of minus 15, and 2xy equals the imaginary component of minus 8. Solving that, we're going to say y is equal to minus 4 over x, and substituting that back up to here, we're going to have x squared minus 16 on x squared. So minus 4 on x all squared is 16 on x squared, and that is equal to minus 15. Timesing everything by x squared, we get x to the power of 4 plus 15x squared minus 16 equals 0. Okay, we can have a go at factorising that. We're going to have x squared plus 16 x squared minus 1 equals 0, which would make x equal to plus or minus 1. Now we can't have plus or minus 4i because we can't have imaginary components to solutions to these equations. So when we're square rooting complex numbers, we're only looking for real answers as x and y. Substituting that into y is minus 4 on x, we're going to have y is equal to minus 4 or positive 4. Now this is important here. We're going to say x is equal to plus or minus 1, but y is equal to minus plus 4. And that's because minus 4 belongs to the 1 solution and plus 4 belongs to the negative 1 solution for x. So the square root of this complex number is, we're going to say plus or minus 1 minus 4i. That's the square root there. Now, if we expanded out that minus, we're going to have minus 1. So we're going to have 1 minus 4i, which is our first solution, and minus 1 plus 4i, which is our second solution. So putting that back into our formula over here, we've got 1 plus or minus 1 minus 4i over 2, which is equal to, if we type into our calculator, 1 plus 1 minus 4i on 2, we get 1 minus 2i, and then 1 minus 1 plus 4i, the second solution, we get 2i. So those are my solutions there. All right, hope that makes sense. That's the square root of complex numbers.